Hello everyone, I'm Cecile Bonifacio from Fischione Instruments doing this tutorial on TEM specimen preparation. Just a brief bio. My background is on TEM, analysis, imaging, and sample preparation, and I've been active in the ISFA conference for the last 6 years. Here's the outline of my tutorial for today. So I have this specimen preparation flowchart and the goals of specimen preparation. And specifically for this tutorial, I'll be talking about more on the focus ion beam technique and other post-fib argon milling preparation and some examples on FinFET device. So this is the flowchart that I'm talking about. So here you can have a bulk material, film, or fibers or nanoparticles as a starting material. For FA, it's most likely a bulk semiconductor device. One thing we want to note is that what type of imaging technique and analysis are you planning to do? What kind of TEM you have. Are you doing TEM or STEM analysis? And also the accelerating voltage of the microscope. One thing to note is that by doing EDS, typically you want to have thicker specimens just because of the volume, X-ray volume that you get more signal for thicker specimen. While in eels, typically you want a very thin specimen to get a really good eels edge. Another thing to consider is the surface to analyze. So this is a schematic for a FinFET device. You can you can get a sample out of a fin cross section, which is in this direction, or you can also get a cross section within the gate oxide in this direction. Another thing is that you can also make a sample in the plan view where all these repeating metal lines are on the surface. So there's some effects on your TM imaging with respect to the surface artifacts. So what you're seeing here is a cross section of a specimen that was milled. So any milling technique, there's seemed to be an amorphous layer on a crystalline material, and these surface artifacts can actually affect your imaging and chemical analysis. So I identified what imaging technique. And as far as specimen thickness, this can affect your dynamical scattering effects, your intensity background in high resolution STEM, and then also in chemical analysis for EELS and FTEM. So the goals of sample preparation is to be able to remove this amorphization damage and to be able to prepare your specimen of appropriate thickness depending on the analysis and accelerating voltage that you'll be using. So some TEM specimen configuration, you can have samples that are prepared conventional way, meaning dimpled or wedge polish. So these are shown here. Fib prepared specimens can be in situ or ex situ lift out specimens. Image on the left here is an in situ lift out specimen on the B post of OmniProbe grid. This is the typical grid that is used for this kind of preparation. And ex situ lift out is typically the lamella is supported on another material, specifically a carbon support or some other kind of material. Another thing is the needle type of specimen. So this is specific for atom probe tomography technique, but mostly the in situ or ex situ lift out is appropriate for semiconductor devices. So let's talk about fib preparation. So nowadays, the dual beam fibs can be a plasma fib, which is one example on the left here, using a xenon plasma ions. Another thing is the gallium fib. So typically, this system, the reason why we call it dual beam is you have an electron source and an ion source in this case. The alpha is the angle between the electron beam and the ion source in this case. So depending on the manufacturer, this angle can change. So this is the example of how you prepare an ex situ specimen. So first, you do the extraction in the lamella inside the fib. So you finish off in the J cut or the U cut. So basically cut free the specimen. And then you take out this bulk specimen and put it on another surface where you have a microscope. You use a glass rod to pick up those lamella, and then start put placing them on carbon support. So an example of this is this quantifoil grid, wherein there's holes inside the carbon support, so that the electron beam can go through it. Another kind of grid would be this specialized grid, slotted grids, where you can actually still do your post-fib polishing, if need be. In terms of in situ specimens, so there are different kinds of specimen. One is an inverted in situ specimen. In this case, you have the silicon substrate on top, and all the metal lines are in the bottom. This specimen can you can achieve very thin specimen in this case. Another is the conventional, typical specimens that you see, where you have all the metal lines on top and the silicon substrate in the bottom. This kind of specimens tend to be thicker, 30 to 50 you can nanometers in thickness can be achieved. The only thing is that you can get curtaining just because of the metal lines on top going into the silicon substrate. Another type of specimen is the planar specimen. So in this case, you have all the metal lines. This device surface is parallel to the TM specimen, so you have repeating features. So that's quite nice for statistics, but there are different applications for this kind of specimen. So now, like I mentioned earlier, you can do gallium fib milling or plasma fib using the xenon beam, and you will get some amorphization damage. So this images here on the top is from gallium fib milling, and then the bottom is from the xenon plasma fib milling. High energy of 30 kV all the way down to 2 kV. What is showing in the middle is this amorphous damage. So in this case, with the plasma fib, you can actually get really good samples in a case where the amorphous damage is only between 40 to 20% less than the gallium fib. So that's one plus of this system. So I just want to note that by xenon plasma fibbing or gallium fib milling, you can get ion implantation. And gallium is quite problematic because you can get chemical reaction or phase changes. In both cases, you can have amorphization damage, which is basically the loss of crystallinity in these silicon materials. You can also get local heating and also some changes on the sample. So that's why it's very important that we actually do the sample prep to make sure that your sample has not changed. So you can have changes in the electronic, optical, magnetic, and thermal properties. So the next few slides will show you the defect and amorphization during gallium fib milling. So initially you have a silicon network that's nicely ordered, right? When you start fib milling using gallium, so what happens, it goes into this network. So what happens is you can have replacement collisions, you can have vacancies, and then also interstitials. And then what happens is this nice network becomes disordered, and that's basically what amorphization is. So these are the specific artifacts that you have to be aware of. Amorphization, gallium implantation, and also alteration of electrical properties on these devices. So typically, we want to make sure that we don't expose your device during sample prep. So what we can do is to lower your energy, okay, when you're preparing your sample, or do a post-fib polishing if necessary. So one thing that you can do is to use argon milling. So argon milling systems, this is usually the broad ion beam systems. And also nowadays we have come up with concentrated ion beam milling systems. So the difference between the two is that the broad beam system uses a millimeter sized beam, well, the concentrated ion beam, you can have submicron to a micron sized beam. So this is quite nice for site specific milling of the sample only. Like I mentioned, compared to the broad ion beam system, it's not site specific, so that can be problematic sometimes. So just a schematic of the two sit to argon milling techniques. So broad ion beam is here. You shine the argon beam onto your sample, millimeter sized beam, and that's how you sputter the material. Concentrated beam is that small argon beam goes into this raster pattern, serpentine pattern, only in the raster box or the milling box that you apply. So the idea is to you decrease the ion energies as you prepare your sample so that you can control your thinning. In this case, we want to do it at 1 kV or below. So here's just an example. Okay, so at 30 kV gallium, remember you're getting this 23 nanometers amorphous layer. So if you want to prepare a 100 nanometer sample at 30 kV, note that 46% of the specimen is actually amorphous. So basically, almost half of it is not the material that you want anymore. Now, if you go to 5 kV and you want to gallium fib milling, you want to achieve 60 nanometers, you still have about 23% of the specimen being amorphous. So significant part of the sample is not what your initial material is, but it's the amorphous layer or artifact. And so by using post-fib argon milling at energies below 500, like at 500 eV, this is showing you if there's sidewall damage or some amorphous damage. This shows you there's none. So this is the best way that you can actually prepare samples without any kind of damage. And the next few slides is an actual example of these. So this specimen is prepared in the gallium fib. So in this case, we want to hit just the fin structure. So we want to go on the gate structure with just the fins. So in the gallium fib, we did a systematic study. We actually look at what's in the front and the back. So we have intermetallic layer on one side and the source and the drain layer on the other side. And then in the TM, so in STEM mode, I tilted the sample, and actually you can count how many fin structures you have and also intermetallic layers. And then you mill the sample at 700 eV. Now you see that, oh, I was able to remove one metallic layer and the fin structure in this case. So then you can estimate what is your milling for each layer. And then if you keep going, now lowering your energy furthermore at 500 eV, now we were able to achieve just the fin structure and some intermetallic layer as we wanted to. So now here's the image at the fin layer, so you can see nicely the silicon dumbbells and the gate oxide layer on top. And this is a 14 nanometer FinFET. And by FTEM, you can actually measure the thickness. So this is an inverted specimen. So you could see that there's some difference in the thickness at the silicon substrate and here in the fin region. So 12 nanometers down below and about 19 nanometers on top. So we have made changes and tried this high tilt argon ion milling. So in this case, you can now see this map. This is a FTEM map where you can actually look at the thickness, and it's quite uniform from the top, the silicon fins here, and the silicon substrate. And I want to note this was prepared as a top-down specimen. Remember, where all you have your metallic layers on top and the silicon substrate, but based on the FTEM analyses, that this technique actually can give you very uniform across the board. So from the silicon fin all the way down to the silicon substrate. So this is one way you can make really highly uniform specimens. So just to summarize, again, if you prepare TM samples to do FA, you want to make sure it's artifact free and it is a representative of the bulk. And one thing you want to do before you do any kind of preparation, you want to make sure that you know what kind of imaging and analysis that you're trying to do, what accelerating voltage. The thing is, at higher kV, let's say 300 kV, that can actually image a 100 nanometer sample. However, if you're using 80 kV, 100 kV, that is quite, you won't be able to image a 100 nanometer sample. That's kind of be very difficult. Another thing is that in this tutorial, I've shown you that you can do fib milling by gallium or xenon plasma fib milling, and also doing a post-fib argon ion milling as the polishing step is the most ideal. In fact, you can get ultra thin samples in this case. And for FA, it's very important to actually have the right thickness for the critical dimension analyses that you're trying to get. For example, for 14 nanometer FinFETs and 7 nanometer FinFETs, you need to have specimens that are 20 nanometer thick or below, just so that you can do your analyses on the gate oxides and other parts of the device. So, with that, I want to thank you guys for listening, and I hope you learned something from this tutorial. And hope to see you sometime in the ISFA tutorial sessions. Thank you.